Welcome to my master thesis presentation for Aalto University. Today I will discuss machine learning algorithms to detect fraud in artworks topic proposed by Blanked. In the agenda, so we'll go about introduction, background. We'll propose two models today, so we'll go and see those two data sets. We'll test the proposed models on the two data sets, and we'll go about seeing the results and the conclusions. Let's start from the problem. Blank, the company that proposed the thesis, is creating a platform that allows users to create digital artworks. And they are willing to provide users with the possibility to create NFTs, which are non-fungible tokens that are saved on the Ethereum blockchain. Artists can earn royalties from the peer-to-peer trade of these. And the problem behind this is that artwork ownership in most NFT platforms is not checked. So it's not uncommon that people mint, so save on the blockchain images that are not, they don't own copyright over it. And my thesis falls around finding a new approach to this and at the same time compare with the current state of the art. So the objective is to detect if an image is violating copyright or not. For the law on intellectual property, we have that copyright is violated when the artwork is a clear copy or a derivative of another work. In academia, this task has the name of image copy detection, and in my study, I have investigated the performances of generative adversarial networks in this context. The research questions are: how do generative adversarial network GAN-based models perform on the task of image copy detection? And how do different GAN-based image copy detectors models perform on different data sets? We'll start by talking about convolutional neural networks, which are the foundation of all we're gonna talk through this presentation. Convolutional neural networks have significantly improved the state of the art in multiple computer vision tasks. And these networks get their name from artificial neural networks and from their layers that perform a mathematical operation of convolution between matrices. In the slides, we can see AlexNet, one of the defining convolutional neural networks, which during the ImageNet competition, a really important competition for image classification, lowered the error rate by 10% compared to the current state of the art that wasn't based on convolutional neural network. And this signed a huge breakthrough. As we can see, the input layer has an image which has size 227 by 227 with depth 3. This image will then be convolved. So there is a kernel of 11 by 11. There are 96 kernels, which are not shown here, which will convolve over the whole image, and they will create an activation map or feature maps. So 96, because there are 96 convolution over it. And these feature maps contain the most important features within the image. And while the sample passes through all these layers, these features get refined and refined until we get to the very last activation map, which contains the key features of the image. And by what we saw in academia, these features are really they boost object detection, they boost image classification, so they're considered good features, and that's what we're gonna try using in our image copy detection. So the convolutional neural network were the base, were the foundation as well for another technology called generative adversarial network. In here, the focus is on the generative model, which generates new images from an adversarial training. So there is a discriminator model and a generator model which compete against each other in a zero-sum game. So the discriminator model can be seen as the art critic able to recognize a copy or a derivative work, and the generator is an art forger trying to produce images that the critic won't classify as plagiarism. So every time at every iteration of the training, the generative model gets always better at generating images, and its objective is the one of generating an image that will pass through the discriminator, and the discriminator will classify that as real. And this is done through min-max loss function, and is minimized using a stochastic gradient descent. So this is the technology that we want to use. We want to see whether the discriminator model trained in this context can provide better discriminative power. In particular, we have implemented a deep convolutional GAN, because one of the main issues with GANs are the training, which was usually unstable and is hard to train. And the authors of Deep Convolution GAN, DC GAN, we'll call it today, discussed how to make the training in GAN more stable by listing a set of constraints in building adversarial networks. And they also proposed this new generative model. As we can see here, we have a vector of 100 containing 100 variables, which is passed through a deconvolution layer, better called fractionally strided layer. So the difference between convolution layers and these fractionally strided layers, that instead of downsampling the the input, they upsample it, so they are able to generate an image of the size that the network needs. And this generative network is the one that we use in our image copy detector. So there are two approaches to image copy detection. One is based on convolutional neural networks as image copy detector. So we train a convolutional neural network on a set of copyrighted images, and then once we train the model, we make it infer from a query image whether this is a violation or not. So this is the first approach. And the second one is done by creating a perceptual hashing as compact representation of the image. So we have an image input. There is a method that, in our case, in the thesis, is based on convolutional neural network. So we extract the features using that convolutional neural network from the image, and out of these features, we create a perceptual hash. So an hash that is able to that has information on the perceptual the perceptual means of the image. And by using these features, we create an hash, and this can be used in image copy detection. We'll see then in this particular context, we'll see where does the features where does the feature extraction comes into play. So here we can see that image copy detection is composed always by two steps, an offline step and an online step. So we have a set of copyrighted images that pass through a feature extractor, in our case a convolutional neural network based on GAN. And so we create a compact representation of it in most cases. And in our case, we'll see that we'll create a hash. We save all this compact representation within a database or a source that is easily queried. And in the online step, what we have is a query image that comes in, a feature extractor, which is always the same as in the offline step. We create a compact representation, and we have a similarity check. So we check whether this compact representation is something that we already seen, which is present into the reference database. And after this similarity check, we determine whether the image is a fake, is a violation of copyright, or is not. In our proposed model, we'll use HashGAN, which is a generative adversarial network composed by a generator, a discriminator, and an encoder that is able to, given a set of images, copyrighted images, is able to generate hashes that are robust to a lot of content-preserving transformations, such as rotation, illumination changes, and so on. So HashGAN is the first model, is the first architecture that we'll use, and then we'll use also DC GAN. So the proposed model with HashGAN looks like this. So we have a query image into HashGAN. HashGAN generates the hash for the image, and there is an hash matching phase, as we saw before. And we compare this with all the hash that we've been previously saved. and we check whether there is a match between the two hashes, and then we determine whether the image is an original or is a violation. In the second case, we have DC GAN that has been trained with all the constraints named in the paper that we presented before. And so we have a query image against the discriminator. The discriminator classifies this as an original or a violation. When it's an original, we have a perceptual hashing method that creates an hash out of the image to double check this first prediction of the model. And then we have a hash matching phase with still the same the hashes of the copyrighted images, and then we determine that this image is an original. Why we do this in two steps is because we don't want images that are violation that are classified as original. We want this rate to be as low as possible, which is important for a fraud detector. The dataset chosen are MS COCO, containing images from different domains and objects, and WBIIS, a dataset that was presented in the context of the evaluation of content-based image indexing architecture, and for that contains a good share of perceptually similar images, and is challenging to try our image copy detector on this, and most state-of-the-art try their architecture on this particular database. What we use 1K, 1000 images from either MS COCO or WBIIS, so we train our models on both datasets separately, and then we augmented this 1K images twice, so we rotated images on 2 different degrees, so 2 degrees and 12 degrees, let's say, and we obtained 6,000 augmented images. And then we did the same for gamma correction and speckle noise. So we have 7,000 images that are trained, that are used to training our models. And then we have the testing. So we have 500 images, new original images. There are as well augmented. And we use this as unseen images to see how do our architecture perform in this scenario. The metrics that we'll use to evaluate our models are accuracy, so true positive, true negative out of all the predictions, and F1 score, which gives us an idea of how well the model balances between precision and recall. So the results on WBIIS, we can see the performance of HashGAN and DC GAN. This GAN reaches a higher than 90% accuracy rate on both speckle noise and gamma transformation, with rotation being the transformation with the lowest accuracy, 71%. While HashGAN, we can see that does achieve an accuracy of average 88% across all scene transformations, so doesn't have a drop when it comes to rotation. And the F1 score shows a really similar picture, with HashGAN being the most consistent model across transformation on WBIIS. Another metric that is important to check is false negative rates. So how many images that are violation are classified as original, something that we don't want. On WBIIS, we have that rotation, 25% of violation images are classified as original. And for speckle and gamma noise, we have more or less 3% and 6% of this rate, which is not really what we want for a fraud detector. While HashGAN has a curious property here, like keeps the same rate of false negative across rotation, speckle, and gamma correction transformation, which is something that is interesting to see. Also, this shows that the HashGAN generates hashes that are slightly different. There are different there are different over the threshold that we set it. So the hashes differ by more than, let's say, 4 or 5 digits, and this generates this false negative. The results on MS COCO are quite similar, we can say. So we see that DC GAN has still a weakness when it comes to rotation, while HashGAN is more stable on those. The F1 score once again shows values higher than 0.9% for all transformation for HashGAN, and a drop um, between and shows a drop between precision recall registered just for rotated images. We can observe that was not the composition of WBIIS dataset to create misclassification in DCGAN, but was still something inherited into the model. So actually, that adversarial network didn't provide a better discriminative power for DCGAN, because as we can see in the previous one, in the previous graph, we have the same drop. We have the same drop when it comes to rotation across different data sets. And when it comes to false negatives, an interesting result, we can see that HashGAN provides 0% of images that are violations classified as original, and which is really, really important for us. And we can also see that the DCGAN commits misclassification up until 7.8% recorded on gamma correction. Here instead is clear how the difference in dataset composition affects HashGAN. While tested on WBIIS, the model is able to generate hashes that are invariant to the degree of transformation present in COCO, meaning that HashGAN here creates hashes that are really similar to the ones that I've seen before. So there is no misclassification when there is a violation. When we compare it to transformation that hasn't been seen, we can see that the F1 score, for example, is higher for DCGAN. So DCGAN is better while classifying images that have been affected by transformation that weren't present in its training set, while HashGAN suffers by this unseen transformation, having 0.3 F1 score and 0.78 F1 score. So we can see here quickly the comparison of current data sets with DCGAN. We can see that the false negative rate increases significantly when it comes to WBIIS. Comparing our models to the state of the art, we can see that DCGAN and HashGAN have lower accuracy rates when it comes to rotation and all manipulations, while when it comes to original images, they are performing better than the perceptual hashing state of the art based on the convolutional neural networks, which is a good result. And the F1 score, we can see that the convolutional neural network as image copy detector performs better in all three cases, so in rotation, speckle noise, and gamma correction. But HashGAN is quite close, so we have 0.9. So with some fine tuning, we can get there. So the conclusions are that for the experiments, the GAN-based solution did not represent an improvement in terms of absolute performances. The classifier used as discriminator influence, the classifier used as discriminator influences more the discrimination power than that versatile training. But GAN-based solutions have the potential image copy detection because in terms of data augmentation and robustness to multiple transformation without the need of high volume of images. So we can generate images, similar images just by using GAN. And in future steps, this can be explored as well as using, instead of the DC GAN discriminator proposed in the model, we can use ResNet, we can use GoogleNet as discriminator to improve the accuracy and the F1 score. And we can use GAN to augment the number of images in the training set that are perceptually similar. And we can also study more the loss used in HashGAN to reduce the hash collision, and how does it approach new transformations to improve that. And we want to evaluate also the performances of HashGAN with different hash lengths. This was it, and thank you.